The Chesapeake Bay is the nation's largest estuary. Chesapeake Bay has a 64,243 square mile watershed that drains portions of 6 jurisdictions: New York, Pennsylvania, Virginia, West Virginia, Delaware, and the District of Columbia. For just a moment, imagine yourself living in the Chesapeake Bay watershed in the early 1800s during a period of great change. As human population has increased in the Chesapeake Bay watershed over the past centuries, land use has changed primarily from undeveloped, forested, to agricultural and developed land. These changes have led to increases in nitrogen inputs. Nitrogen and phosphorus are major macronutrients necessary for plant growth. But in excessive amounts, these nutrients can create increased algae growth, decay, and low oxygen for aquatic life. In 2011, this increased algal productivity from nutrient enrichment, often termed eutrophication, resulted in the most expansive low oxygen or hypoxia conditions, also known as dead zones, in the Chesapeake Bay. In fact, hypoxic volumes in the Chesapeake Bay have increased since the 1950s. In 2010, the largest total maximum daily load, TMDL, in the nation was developed for the Chesapeake Bay for nitrogen, phosphorus, and sediment. These pollution allocations were further divided by major river basins and states. Management practices, expected to eventually reduce nitrogen by 25%, are set to be implemented in the Bay watershed by 2025. These proportional sources of nitrogen load delivered to the Chesapeake Bay varies by state. The Chesapeake Bay watershed consists of 6 major river drainage regions that contribute varying stream flow to the bay. Land use in the Bay watershed is predominantly undeveloped, along with agricultural and developed areas. Before we talk about the various drivers of change that affect the delivery of nitrogen to the Chesapeake Bay, let's define some important terms and units of measurement. Watershed, a land area that drains rainfall to a water body, such as a stream. Concentration, the mass of nitrogen in a known volume of water, often measured in milligrams per liter. Load, mass of nitrogen delivered for a given time, often measured in kilograms per year. Yield, the load of nitrogen relative to the contributing landscape or watershed, often measured in kilograms per square kilometer per year. And flow normalized load, adjusted nitrogen loads for flow and season, often measured in kilograms per year. Let's also review the major sources of nitrogen and how it's cycled around the Chesapeake Bay watershed. Lastly, it's important to understand the magnitude of those sources as inputs to the watershed and exports to the bay. Those responsible for management decisions have varying degrees of influence on the changes that control the movement of nitrogen. We are now ready to discuss the various factors that affect the delivery of nitrogen to the Chesapeake Bay. Local resource managers have less control over the climate and hydrology. So let's talk first about climate and how increasing concentrations of greenhouse gases like carbon dioxide that trap heat close to the Earth's surface has caused increases in mean annual temperature. Climate scientists use four major emission scenarios, representative concentration pathways, or RCPs, of 2.6, 4.5, 6, or 8.5 watts per square meter for how increasing amounts of greenhouse gases could trap heat. The mean annual temperature across the entire Chesapeake Bay watershed is expected to increase by 2 degrees by 2050 compared to 1995, with larger differences likely in the northernmost part of the watershed. Projected precipitation changes from 1995 to 2050 for the Chesapeake Bay watershed show a 6.3% increase in the average annual precipitation, with the largest increases occurring in the southern states. Overall, the Chesapeake Bay is experiencing a warming trend, which shifts to drier summer and fall seasons, followed by wetter winter and spring seasons. The components of the hydrologic cycle, precipitation, evapotranspiration, runoff, recharge, groundwater discharge, and streamflow, store, process, and ultimately transport water and nitrogen to the Chesapeake Bay. Continued warming trends are projected to produce less snowpack and early runoff in the winter versus the spring, followed by less of a change in runoff during the summer and fall. These seasonal shifts in surface runoff will affect nitrogen export to streams. Let's also remember the groundwater transport of nitrogen. The time it takes for groundwater and nitrogen to reach streams, often referred to as lag time, can range from days to years. This means that even in some areas, the effect of management actions to reduce nitrogen may not be realized for decades to come. At the regional level, local resource managers also have less control over atmospheric deposition and land use changes, driven often by population growth. Emissions can lead to the atmospheric deposition of nitrogen, wet and dry, downwind from the sources after being transformed and transported in the atmosphere. Atmospheric oxidized nitrogen deposition across the Bay watershed has shown a declining trend since the 1990s. largely due to the air quality management actions required by the Clean Air Act. Whereas chemically reduced nitrogen deposition across the Bay watershed has shown a slight decline or no trend. About half of the oxidized nitrogen emissions that contribute to the atmospheric deposition nitrogen loads to the Chesapeake Bay originate from an airshed that is much larger than the actual watershed. Atmospheric deposition of nitrogen is widespread across the Bay watershed. The highest values occur in developed areas such as Washington, D.C. and Baltimore, Maryland, and areas of intensive agriculture such as southeastern Pennsylvania. Regarding land use, since 1950, the population growth has increased exponentially in the Bay watershed, generating activities that have produced excessive nutrient and sediment inputs to rivers and streams. Since 1985, development has occurred mostly at the expense of natural and agricultural areas, such as pasture and cropland. If the trends of the 1980s through the 2010s continue, then future growth will be focused in suburban and adjacent counties, with an emphasis on developing large lot, single-family homes. Local resource managers have most control over agriculture and development. Since 1950, acres in farmland has decreased, but crop and animal production has remained relatively constant due in large part to the intensification of agriculture. For example, there has been a substantial increase in the number of broiler chickens sold in the Chesapeake Bay watershed from 1954 to 2012, and selective breeding and nutrition improvements have more than doubled the weight of broilers. This has led to increases in nitrogen-related impacts to water quality in agricultural areas. For instance, nitrogen concentrations in streams of the eastern shore of the Chesapeake Bay commonly exceed water quality criteria recommended to protect aquatic organisms. There has also been an increase in the variety and the quantity of conservation practices to reduce nitrogen from agricultural areas. An expected eventual nitrogen reduction of 11% from 1985 to 2014 has been estimated for conservation practices and land retirement. Despite these estimates, nitrogen loads to streams in most agricultural areas did not change substantially during this period, possibly due to the lag time needed to see the effects of nutrient reduction efforts. More research is needed to better understand the water quality response of conservation practices for planning. The expansion of developed land is also a major driver of nitrogen in the Chesapeake Bay watershed. Nitrogen from point sources such as wastewater has declined, controlled through regulations and technology, and will likely continue to be important in controlling nitrogen loads in urban streams. Management of non-point sources such as stormwater of nitrogen has been a recent focus and will likely continue as urban centers expand across the watershed in coming decades. Now let's look at some examples of how these factors affect the delivery of nitrogen around the Chesapeake Bay watershed. The Patuxent River demonstrates the clear connection between improved wastewater treatment and nitrogen loads. Pine Creek, the main source of nitrogen to this forested watershed, is from atmospheric deposition, which has been decreasing since the 1980s. As a result, Pine Creek has shown a reduction in nitrogen exports. Difficult Run, an urbanized watershed with increasing nitrogen loads, most likely as a result of septic discharges and new construction. The Choptank River, nitrogen loads originating from mainly agricultural fertilizer have continued to increase despite conservation efforts owing to the long groundwater transit time of legacy nitrate contamination. And the Susquehanna River, a large watershed that has shown a promising decline in nitrogen loads since the 1980s as a result of improvements in wastewater and implementation of management practices. But loads have remained consistent in recent decades. Overall, total nitrogen loads have decreased from the major rivers to the Chesapeake Bay. The Susquehanna River, with the largest annual load over time, continues to be a major challenge with respect to reaching the goal of TMDL. Before you go, let's look at a long-term perspective of the major drivers of nitrogen change up to the present and a forecast into the future for the Chesapeake Bay watershed. The sum of all sources of nitrogen to the bay increased substantially from 1950 until the 1980s, but varied afterwards. Nitrogen from atmospheric deposition and wastewater increased substantially from 1950, but started to decrease in more recent decades owing to the effects of the Clean Air Act and implementation of enhanced nitrogen removal technologies. Nitrogen from developed areas has increased along with population growth, and this trend is projected to continue. Nitrogen from agriculture has continually increased from 1950 owing to the widespread use of chemical fertilizer and manure from the intensification of animal agriculture in some areas. Future scenarios for agriculture, which is the largest source of nitrogen in the watershed, include both increasing and decreasing amounts from fertilizer and manure sources, and suggest that the export of nitrogen to the bay presents a challenge to nitrogen load targets. In summary, the greatest opportunities for nitrogen reductions to the Chesapeake Bay are in developed and agricultural areas. There are numerous coastal areas around the world that have been impacted by excess nitrogen. The science, management, and regulation efforts to save the Chesapeake Bay are unprecedented, and if the nation's largest estuary can rebound, it will serve as a model for the world. For more information on the science provided in this presentation, please reference the following U.S. Geological Survey publication, Nitrogen in the Chesapeake Bay Watershed, A Century of Change, 1950 to 2050. An audio-described version of this presentation is available at